In this lecture, we'll consider the problem of how you can map one subset of the complex plane onto another by an analytic function. So suppose that we have some set here and another set here. Can we find an analytic function which will map this set bijectively onto that one? This problem of finding such an f turns out to be very important in many applications, and it's also interesting for many theoretical purposes. For example, there is a very non-trivial theorem which is called the Riemann mapping theorem. Which says that every simply connected set in the plane, except for the whole plane itself, is conformally equivalent to the unit disk. That is, you can actually find a analytic function which is a bijective map of the unit disk onto that set. However, even if we know in theory that such a map exists, it can be quite difficult to find it. For example, even if you take the very simple problem, what you could think would be a simple problem of mapping the unit disk onto the interior of an elliptic curve like this, that turns out to be very difficult. Nevertheless, it's part of every mathematician's toolbox to be able to construct maps in simple cases between different subsets of the complex plane. So before we start looking at explicit problems, there's a very important property of this kind of map which I want to consider now. So, which is also the background for the name conformal. So the idea is that if you take two curves here in this set and they intersect at a certain point, then the tangents to these curves, they will form a certain angle here now. And if you now map these curves here onto by this bijective analytic function, you can map these curves onto other curves in this region. And the curves will, of course, look very different in general, but the angle between the tangents here will be the same. So analytic functions in general preserve angles between curves, you might say. So why is this? Well, if you consider the curve over here to be given by z is equal to z of t, then of course the direction of the tangent is given by, you take the derivative of this curve here now, and if you take the argument of this derivative, that will give you the direction of the curve here now. If you consider the curve you get by mapping by f, then you get a curve which you can write as w of t, which is equal to f of z of t then. And of course, the direction of the tangent of this composed curve will also be given by the argument of the derivative of w. But the point is that if you take the derivative of this composed curve here now by the chain rule, you will get that this derivative can be written as f prime at this point z of t, times the inner derivative, which is z prime of t then. And by the properties of the argument function then, you see that this product, when you take the argument of the product, you will get a sum of two terms here now. And if you now consider this point where this intersect, if that is t naught, then if you now insert t naught in this relation here now, then you see that what happens to the direction of the curve here is that the direction is given by taking the original argument of the curve over here, and then you add this fixed number to the argument. And this number that you add is independent of the curve. It just depends on the point and the function f. So this means that every curve passing through this point will be turned by this map by the same angle, this one. And from this it immediately follows that angles between curves will of course be preserved. Okay, so now we go on and, well, before we go on, I'll just give one more comment to this. It's an important fact here now that this formula is true as long as you have this situation where you have a bijective analytic function and so on. But if the derivative of f is equal to 0 at a point, then this is no longer true. So you can consider the example where you map z to z square. Then in the complex plane, if you take the curve, which is the real axis here now, it will be mapped onto the positive real axis, of course. But the imaginary positive part of the imaginary axis will be mapped onto the negative part of the real axis. So here you see that this angle, which was a 90-degree angle, will be mapped onto a 180-degree angle. So this is, of course, because this mapping here now will have a derivative which is 0 at the origin. This is exactly why this can occur. At every other point, this map will also preserve angles now, but not at the origin. So let us now consider the problem of finding explicit maps between different regions. And to do that, we first return to the Möbius maps that we already met in the beginning of the course. So let me recall that what a Möbius map is. Well, a Möbius map is a map of the following form, where we now suppose that AD minus BC is different from 0. Well, if this would be 0, then the function would just be a constant, which is non-interesting then. But as long as this is fulfilled, then this will give you a bijective map of the extended set of complex numbers onto itself. So the extended complex numbers, remember, that's the complex numbers and together with the point at infinity. So this can also be viewed as a Riemann sphere then. So every Möbius map gives you a bijection of the of the extended complex numbers or the Riemann sphere onto themselves. Also we have an important property of Möbius transformations, which I'll recall here now. Every Möbius transformation or map takes circle and lines to circles or lines. So if you take the image under this map of a line, you can't be sure that the image will be a line. But if it's not, then it will be a circle. And the same thing for a circle. If you take the map, the image of a circle under this map, then you can't be sure that the image is a circle. But if it's not, then it will have to be a real line. And this property makes Möbius maps very useful for mapping certain sets onto each other. For example, the simplest case is when you want to map, say, the unit disk onto the upper half plane. So how do we construct the Möbius map which will take this unit disk onto the upper half plane? Well, one of the nice things about Möbius transformations is that they are determined once you specify where 3 different points should go. Because you have just 4 constants here to determine, and this well, actually, if you multiply all constants by the same constants, then you get the same Möbius map. So essentially, there are only 3 constants to determine here, and each point which you demand should be mapped to a specific point will give you 1 condition. So 3 conditions, that's enough to determine a Möbius transformation then. So if we want to map this unit disk onto the upper half plane, then obviously we should map the boundary of the unit disk, that is the unit circle, onto the real axis. And so if we choose 3 points on the unit circle, for example, these 3 points, then, and map them onto 3 points on the real axis, then we can be sure that the corresponding Möbius map will take the whole circle onto the real axis. And to do this in a convenient way, it's also convenient to include the point at infinity as a point on the real axis. So the way we do it here now is we take this point -1, and we'll say that we'll map -1 onto 0 then. And then we take the point here -I, and we want to map the point -I onto 1 here. And then we take the point 1, and we want to map it onto the point at infinity. So how do you construct a Möbius map with these properties then? Well, there is a standard way of doing this, which is called the cross ratio sometimes. So you can actually consider this expression here now. So here Z is the variable, Z1, Z2, Z3. That's 3 arbitrary points. And then you observe that Z1 will always be mapped to 0 now. Because if you insert Z1 here, you will get this factor 0. Z2 will always be mapped onto 1, because if you insert Z2 here, then this factor cancels out against that one, and this factor against that one. And if you insert Z3, then this will be mapped onto infinity, because you get a 0 in the denominator here now. So in our case, Z1 is just -1, Z2 is -I, and Z3 is just 1. So we'll get T of Z is equal to Z minus -1, that is Z plus 1. And here you get Z minus 1, so Z minus 1 here now. And then here you get minus I minus Z3. Z3 was 1, so that's minus I minus 1. And down here you get minus I minus Z1, which is plus 1 then. And so if you just compute this expression, you will see that this will give you minus I times Z plus 1 divided by Z minus 1, or if you like, I times Z plus 1 divided by 1 minus Z. So this is obviously a Möbius transformation, and we know that it maps this circle onto the real axis. But of course, there are two possibilities now. It could be that the interior here is mapped onto the upper half plane, which is actually what we want. But it could, in principle, also be that the interior here is mapped onto the lower half plane. In both cases, the boundary here would be mapped to the boundary here. So let's check that this is the right one. And this you do by inserting, say, the point, any point here in the inside, like the origin. If you insert that here, you see that the origin will be mapped to, well, you get 1 divided by 1 here now. So this will be mapped to the point I there. So obviously the interior here is mapped onto the upper half plane. Actually, there's, if you don't want to, you don't have to consider an extra point here. You can observe that if you follow these 3 points from Z1, Z2, Z3, and if you have if you go this way and you have this domain on your left-hand side, as in this picture, then the mapped region will also be on your left-hand side when you go in from go through the image points in the same direction, from the image of Z1 to the image of Z2 to the image of Z3. Then you see still that this upper half plane will be on your left-hand side. Okay, so this is a simple example of how you map one region onto another one. Of course, there are very many other examples, and the more of them you know, the better you can do this. So one example we had here, this map taking Z to Z2 maps the first quadrant onto the upper half plane, for example. And in fact, if you take any sector-like region here now, with an opening angle alpha here now, then you can map that onto a half plane by the map which takes Z to the power pi divided by alpha. And there are many other examples also. If you, for example, take any rectangle in the plane here now, then you can map that onto a region of this form by using the exponential map. And there are lots and lots of others, and nobody knows them all, but the more you know, the better, so to speak. So let me now just finish up here now by giving one explicit example. Suppose we take the set of all complex numbers with the property that z minus 1 absolute should be less than 1, and we want to map it onto to the first quadrant. Well, how do you do that? Well, the usual procedure is that you try to build a map like this up in several steps. So the first step here now, taking z to z z minus 1, will map this disk now onto the ordinary unit disk. Then we can map the ordinary unit disk onto the upper half plane. We already know how to do that. We can use the Möbius transform we just constructed now. Remember that this Möbius map was given by T of z is equal to I times z plus 1 divided by 1 minus z. So if you just consider the composition of this now, we'll get that this we'll get the composed map here now, S of z, which is equal to I times z minus 1, so you get z up here, and then 1 minus z minus 1, so it's 2 minus z down here. But then we have mapped this onto the upper half plane, but we wanted to map it onto the first quadrant. And we know the inverse map of that. We know how to map the first quadrant onto the upper half plane. That was just a square map. So to map in the other direction, you have to take the inverse of the square map, which is the square root map. So finally, the final composition here now will be the map which takes this number onto the square root, say the principal part then, of the square root function. So this map will now take this circle here now onto the first quadrant. And there are very many similar mappings that you can study in a similar way.